Okay, so I think we're recording now. So what I'd like to do today is we're going to cover some basics of MRI, and um, this is a course primarily on fMRI, but I think it's useful for most people to know something about MRI if you're going to be in this area. So obviously we can't cover all of MRI in one lecture, and we're going to probably spend about 1.5 lectures covering what I consider the bare minimum of MRI you need, and then we'll transition to fMRI. Okay. So there's a lot of key concepts for today, and I'm not expecting you to be an expert in any of these, but today's really more just exposure of different concepts. Okay. And then we'll have some exercises sort of halfway through to sort of gauge some understanding. So hopefully most of you have seen an MRI system, and so it's really sort of this big, or at least the MRI systems that we have here are these big donut-shaped machines, and the main thing is they have three main coils. There's the radio frequency coil, there's the gradient coil, and then there's the main magnet coil, and this is by far the largest coil. Okay. And that coil the job of that coil is to create a really strong magnetic field. And typically we have lots of liquid helium to keep it super cool. So it's made up of superconducting wire, and so that sound you hear in the magnet room, that ba-bump, 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 that is the helium pump, which basically is trying to, as the helium boils off, it tries to condense it back, because helium is a very limited resource. A few years ago, you might have noticed that the price of helium balloons went up because there was a scarcity of helium. Okay, so towards that end, there are sort of people trying to develop magnets that require much less helium. But for now, for example, the magnets we have require quite a bit of helium. Okay. So to give you a sense of how strong these fields are, we talk about these main magnetic fields in terms of Tesla. Okay. And so the unit that you'll hear is Tesla. So when someone talks about these scanners here, we have 3 Tesla or 3T systems. So how strong is a Tesla? Well, Tesla is 10,000 Gauss. Okay, so how strong is a Gauss? The Earth's magnetic field is about half a Gauss. Okay, so when you have a compass needle and it points in the Earth's magnetic field, you're measuring something that's half a Gauss. Okay, so that means we're tens of thousands of times stronger than the Earth's magnetic field. Okay, so a 3 Tesla field would be about 60,000 times stronger than the Earth's magnetic field. Okay. So for example, here, and the interesting thing is the field does change depending on where you are in the world. So here in San Diego, it's about half a Gauss. Okay. But it's changing as the Earth's fields sort of rotate. So these are the scanners we have here at the center. We have 2 3 Tesla systems. But those are by far not the strongest systems in the world. So there are probably about 100 of these now, 7 Tesla systems. There's one at Chicago, 9.4 Tesla, 10.5 Tesla at University of Minnesota, and 11.7 T. I think the only one that's working, these are working, and this one is working. The rest are still having lots of problems. Okay, it's very difficult to build these very big magnets. It's a lot of magnetic field. Okay, so I'm not going to go over this video, but it's sort of fun to watch on your own. So it'll convince you how strong the Earth's magnetic field is, and then if you take Aaron's safety course, you'll be even more convinced that you need to be very careful around the magnet. So we've talked about sort of this part here, the main coil. The next part is the RF coils. Okay, and so typically there will be what's called a body RF coil, and that's also just a big cylinder that goes around the whole body. And there can be smaller coils, like for example a knee coil or spine coils, and there can also be, later on we'll talk about like head coils. Okay, so we're going to talk a little bit about the RF coils. So the main body coil its job is to transmit RF energy into the sample. Okay, and so for most of fMRI, we will be using this for the fMRI for transmit. Okay. Now you could use the same coil to receive the signal back, but the sensitivity is not going to be very strong. And so typically for most of your fMRI experiments, you're going to transmit with that body coil, and then you're going to receive with a head coil. All right? I need to change the preferences on my power savings, but we'll do that later. Okay. All right. So this is what a transmit coil looks like. So it's just a bunch of wires, and what it does is generates radio frequency magnetic field that is used to what's called excite the spins, and we'll talk about what that means in a little bit. Essentially, it's putting energy into the system. Okay, so it's stimulating the system, and then later on we're going to receive and listen to the system. Now, we talked about head coils, and so those of you who have done experiments here have either probably used the 8-channel head coil or the 32-channel head coil. Okay? And each of these is actually, if you were to strip them apart, they would look something like this. Not exactly, but they're made up of little coils. Okay, so the 32-channel coil actually has 32 different coils in it. The 8-channel has 8 different coils in it. All right, and we'll talk a little bit about why there's some advantages to using something that has multiple channels. Okay. So interestingly enough, this was the prototype version of the coil that is now the Siemens product coil. Okay, so this was the, before it became a product, it looked like the thing on top. The last component that we have to talk about is the MRI gradients. Okay, and for those of you who've done MRI or been in the MRI or run MRI studies, this is the part that makes the biggest sound. Okay, this is the part that the subjects complain about. Oh, MRI is too noisy. And these are, there's 3 different coils. There's one for the X, Y, and Z. And these are going to create what are called magnetic field gradients in each of those directions. All right? And these are what allows us to make the images. All right? Without these gradients, there would be no MRI. Okay? With just the main field and the RF coil, you can do NMR, which is nuclear magnetic resonance. So in chemistry, you might hear about NMR, and so you can do spectroscopy. But to do anything related to creating an image, you have to have these gradients. All right? So what is it? These are sort of pictures of what the gradients look like, and what do the gradients do? They basically make it so that in sort of an MRI system, if you have the main field, it creates a magnetic field, what we call B naught, that's very strong along the vertical axis. So we call that's along the Z direction. Okay, and so the gradients add on to that main field. Okay, and so for example, they might, if I have a Z gradient, it's going to add a field that gets stronger in the Z direction. Okay, so it's getting stronger in the Z direction. Or if I add a Y gradient, it's adding a field that gets stronger in the Y direction. Okay. But notice I'm always talking about adding on to the Z component of the field. Okay. This is from the book, and it's showing sort of an idea of what the gradients are doing. So in the MRI system, X is typically left to right, and so you're seeing the field varying from left to right. Y is typically A to P, so you're seeing the field vary A to P, and Z is inferior to superior. Okay. So I'm going to use terms like coronal, sagittal. So one of the, I'll post another PDF from, or one of the primers from this book goes through some of the basic terminology. So hopefully everyone's familiar with it, but if not, we'll post that. All right. Any questions up to now? Okay, so these gradients are really super strong. So they create very quick changes in the magnetic field. Okay, and so when you're in the scanner and you hear all that buzzing and all that sound, it's because these fields are switching back and forth really, really quickly. Okay, typically hundreds of thousands of times per second. Okay, and or thousands of times per second. So they're basically in the audio frequency range, right? And in fact, you can actually use these coils to make sound. So you can actually, I don't think I put the video in for this, but you can actually have the gradients talk to you, okay? And that means that these are actually essentially very similar to the amplifiers that are used in rock concerts. So for example, these gradients here are 1 megawatt of power per channel. And back in 2017, I looked up, or 2018, I looked up, there was some statistic for the Metallica 2017 World Tour, and that was like, this rock concert in a stadium, and that was only 367,000 watts. Okay, so we have much more energy in these than there are in these rock concerts. Okay, so it's a lot of energy. Okay, so when you come in one day and the gradient amp has blown out, that's why, because these are really very, very powerful amplifiers. So so putting it all together, it's a really complicated machine. That's why it's sort of remarkable that it only fails once in a while. And so we have the magnet, we've got the RF that's going into the RF coil, and we have the gradient system that's driving the gradient coils. All right. So that's the overview of what an MRI system looks like and how it's built. And so if there's no more questions, we're going to move on into some MRI physics. So are there any questions before we move on? Yes?
What are the benefits between using the 8-channel versus 32?
Yeah, so we'll get into that a little more, but the 32-channel allows you to go faster is the main reason why it's really taken over. It offers a little more sensitivity at the cortex, but the main reason it's become the de facto standard is because you can do something called multi-band imaging, which we'll touch upon probably at the very end of this lecture. Okay? Or we'll actually talk about it in just a few slides probably, and then go over it again. So there's really 4 main steps to an MRI system, and so we're just going to give you a brief overview of all those steps. So, and each of those steps corresponds to one part of the hardware. So the first thing that you always need is you need this magnet. And what the magnet does is it creates polarization. Okay? It creates enough magnetization that we can work with. Right? The next step is the RF coil, and there's involved in both transmit and receive. On the transmit side, what it does is excites the magnetization, and then we'll talk about why that's important. As we talked about, the gradients are what's really needed for creating the image, and that's what we call encoding. And then the RF coil is also receiving, and mathematically it's actually doing what's called integration. So let's talk a little bit about spins. Okay, so this isn't the physics course, but the basics of MRI and fMRI is spins, and it is going to be useful to understand a little bit about spins if you really want to have an intuitive understanding of MRI. So spins are an intrinsic property of elementary particles. It's basically their intrinsic angular momentum. So one way to think about it is if you have a sphere rotating around its own axis, that's like a proton rotating around its own axis. That proton, you could say, has both charge and it also has spin. So it's got some angular momentum. Okay. And so it turns out that that charged particle rotating around its own axis creates a magnetic field. Okay? And so these particles have angular momentum and they also create their own magnetic field. Okay? Now, it's not every different protons, different atoms have different spins. And so the one we use primarily in fMRI, almost exclusively, is the hydrogen proton. And we're lucky that it has a spin of a half because otherwise there would be no MRI or fMRI. Okay. Now you can look at other things. You can look at phosphorus. You can look at hyperpolarized carbon. You can look at carbon-13. You can look at sodium. You can use fluorine. But all of those are really have very minute concentrations in the body compared to water. So primarily what we're going to be doing in fMRI is we're looking at the properties of the hydrogen proton. Okay. So one thing to realize about, if you think about all these little protons in your body, okay, so you imagine you have all these protons in their body, and they all have their own intrinsic angular momentum. And so right now in your body, you have all these little magnets in your body. Okay, all the protons in your body are little magnets. Okay, and we're all in the Earth's magnetic field right now. Okay, and let's say, which way is north? That way? Okay. So the Earth's magnetic field is that way. Okay. So which way, if we had a little compass needles, all had little compass needles here, which way would the compass needles point? They point that way, right? So in fact, on average, if we were to average all your spins in your body, right now they're pointing that way. It's not very strong, but there is a tendency for them to point in the Earth's magnetic field. Okay? And you can actually do MRI with the Earth's magnetic field. It's just you don't have much sensitivity. Okay? So I know, like in Siberia, they used to build these big coils, and then they were looking for oil, and then they would use the Earth's magnetic field to just look for oil. Okay? So there is going to be a tendency for magnets to align with an external magnetic field, right? So the rate at which they align is governed by what's called the Boltzmann distribution. So this is a probability. There's much more probability that they'll align with the magnetic field than away from the magnetic field, and less probability they'll align perpendicular. So there's a slight probability, but it's not 100% probability. It just falls off exponentially. Okay. So a useful way to think about that is if you think about, like Gilman parking structure or Osler parking structure, right? Let's say there's like no S, A, or B parking, right? You could park anywhere you want, right? So you come in the morning, and most people will just park on the bottom level, right? I mean, now some people might want to park on the top for some reason, or do they have they're really excited, they'll just keep driving and go to the top, okay? But if you look at the different levels of the parking garage, in general, the lowest energy states will be occupied more than the high energy states. The same thing happens with spins, okay? Most spins will prefer to be in their lowest energy state, but some will be in a high energy state and falls off exponentially. So if you look at spins, so this is a collection of spins, and in the absence of any applied magnetic field, they're all going to be randomly pointed in different directions. Right? So if we think of each of those vectors, and we pulled all those vectors and had those as arrows, and then put all their, sort of the bottom of all those vectors at the middle of this like ball, then all those vectors point in different directions. And so what's going to happen if I think about summing up all those vectors? What's the net sum going to be? 0, right? So if I think of vectors pointing in lots of different directions, they're going to cancel each other out and sum to 0. Okay. Now, if I now apply a really strong magnetic field, for example, like a 3 Tesla magnetic field, what happens is there's a preference for the magnetization to point along the magnetic field. They're not going to perfectly point, but the higher probability they're going to point with the magnetic field than against it. So now when we sum up all the vectors, we get what's called a net magnetization. Okay? And that net magnetization we call m sub naught, and it is proportional to the magnetic field B. And that's why people always try to build bigger and bigger magnets, because we're trying to make that magnetization bigger. So that's the basis of our signal. The bigger we make the magnetic field, the bigger our signal is. Okay? And so that's why people go from 1.5 Tesla to 3T. That's why people are now trying to move fMRI from 3T to 7T, okay? Because there is more signal that you can work with. Okay? So especially if you're trying to look at really small structures in the brain, there may be a potential benefit to going to 7T. There's a lot of problems, but there's a potential that you can do things at 7T that you can't do at 3T. Okay? So it's 2.5 times stronger magnetic field, so 2.5 times stronger signal, okay? Which is a lot. Okay, any questions? Okay. The next concept, and I forgot to bring my bicycle wheel, but I'll bring it next time. So I think there's a video here of the guy doing it, so we'll just play the video. The next thing you need to know, and this is actually probably one of the more important concepts to have in terms of understanding MRI and diffusion imaging and different types of neuroimaging based on MRI, is spins not only have a magnetic field, but they have angular momentum. And so they precess around magnetic fields. So they do this sort of motion, okay? So let's see how this video works. So he's going to take this wheel, and he sets it spinning. First of all, he does that. And he sets it spinning at some point. And then it goes around like that. Okay. So it's got angular momentum, it's got weight, so in this case gravity is the force, and it spins around. Okay. So this is also why you can ride a bike and not fall over. Okay. I'll try to remember to bring the bicycle wheel for Wednesday's lecture because it's much better if you do it in person. But the idea is spins precess. Okay, so spins are always going around the main field, right? And that's really, we're going to take advantage of that in both making the MRI image and also doing fMRI. And it's also going to be a very important component for diffusion imaging. Okay. So how fast do they go? They go pretty fast. So for this lists for different field strengths, the frequencies, and the frequency is what's called the Larmor frequency, and it's proportional to the main magnetic field through a constant called gamma, or the gyromagnetic ratio. And for a 3 Tesla system, the frequency is 127 megahertz. Okay, so so the way to think about that is when we put you into the 3T scanner, first of all, your spins get aligned. That's why some people think it's therapeutic to align the scanner, but it's like new age therapy, right? You can align all your spins, right? So who knows if that's true or not? But that's what happens. Your spins are somewhat aligned with the 3T field. The other thing that's happening is the spins are all precessing, and they're going 127 million times per second around that field. You don't feel anything, obviously, but that's what they're doing. When we take you out of the scanner, and now they're in the Earth's magnetic field, so they're precessing much more slowly. Okay. They'll only be going about 2,000 times per second. Okay. So these frequencies, so for example, a 1.5T system would be at 65 million cycles. KPVS FM's at 89.5 megahertz. Civil aviation bands are 127 megahertz. So that's why we have to close the door, and we have to have copper. So those rooms are shielded with copper, because any radio frequencies that get into that room will be picked up by the system, and they're right in the frequency range that we're looking for, which is the frequency that the spins are precessing at. Right? So that's why it's important that the door is closed. If there's a problem with that ceiling, you can get artifacts in your image. Okay, so the next part we're going to talk about is RF excitation. So RF stands for radio frequency. And this is basically, as I said, the spins are primarily aligned with the main field here. Okay. So the spins are like this. And it turns out it's really hard to measure what these spins are doing. What we want to do is we want to tip them away from their equilibrium position, and now they can precess around like that. And it turns out now they're creating this time-varying magnetic field, which we can pick up using just a simple loop of wire. Okay, so that's why we have to tip the spins. Okay, and so the idea behind RF excitation is we take the spins from here, and then we try to convert them here. And in this case, we've tipped the spin 90 degrees. Okay, so this would be a 90-degree flip angle. So when you're at the console and you're setting the flip angle, that's what you're doing. You're deciding how much are you tipping those spins over. So you could do like 30 degrees, 45, 90, 180. You do whatever you want, but you're basically tipping those spins over. Okay. So how do you tip the spins over? Well, the idea is it's very similar to what would happen if you, I don't know what this person is doing with their car, but so let's say you had this car in your backyard and you put it on a swing, right? And this car weighs 2,000 pounds, right? And my task for you is I give you a little straw, right, a paper straw, and I say, using this straw, I want you to get this car moving back and forth with like a 1 second period. Go back and forth in a second. So I want you to going back and forth, and it has to move back like, within plus or minus 1 foot. Okay, and it's a plastic straw, so you can't push very hard. So how would you get this thing going back and forth? Any ideas? Let's say I offered you $1 million and you could do that. So you're given a straw, and I want you to get this thing moving back and forth, so it goes plus or minus 1 foot. And actually, I don't care what frequency it goes. I just want it to go back plus or minus 1 foot. Okay. With very small pushes. So obviously, you're going to break the straw if you push too hard, right? So how should you push that car? You guys can talk about it amongst yourselves. Any ideas?
Like it's a trick question.
Well, it's doable, right? First of all, is it doable?
Yeah.
Okay, so how would you do it?
Well, you push the car with the straw.
But how would you push it?
This way.
Okay, but would you, what would be the timing of your pushes?
Timing?
Yeah. Like, you can't push it too hard because you're going to break the straw, right? So each time you push it, you can push it a little bit, right? But what should the timing of the pushes be? Fast? Okay, how fast?
Per second?
Okay,
That'd be really fast.
let's go back to something. Has everyone here has been at the playground, right?
Mm-hmm.
And so let's say there's, when you're really small, let's say your dad's on the playground or your mom's on the playground, or there's some huge kid on the playground and they're on the swing. How do you push them?
Rhythmically?
Yeah, you got to do it rhythmically, right? What's the rhythm you need to push them at? Yeah. Otherwise, you're going to break your finger, right? If you push them at the wrong time, right? If you push them as they're coming back at you, you're going to break your fingers, right? So you have to push them at the resonant frequency, right? So there's going to be, on a swing, there's some resonant frequency. Okay. For this guy, there's some length L of this pendulum. There's gravity G, and so the frequency is actually proportional. I think it's like G over L or something like that. There's some formula from physics, okay? So for that system, there's a resonant frequency, okay? For spins, there's also resonant frequency with the Larmor frequency. Okay, so it turns out that getting the excitation is similar, the RF excitation is similar. We use a very small RF field to perturb the spins away from equilibrium, and then we sort of follow them along as they spiral down. Okay. So this is what RF excitation looks like. So if you notice that this is the RF field, which we call B1, and you notice this is going to, and the spins are going to process at a certain frequency. So you notice that RF field is going to process at the same frequency as the spin. And as it does that, it can get the spin to sort of rotate down. Okay. And here, if the RF field is not at the right frequency, then we never get the spin to come off. Okay. So there is this concept that we're using these, we have to apply these excitation fields at the right frequency to excite the spins. And so if we do that, we go from sort of this, what we call longitudinal magnetization, in this case, to transverse magnetization. So we're taking the spin, in this case, 90 degrees. Okay. So now we do that, we're going to tip all the spins. Okay. So that's what would be, so if we do that, we just do that, like we tip all the spins. And that's what we do if we want to do 3D imaging. So we tip all the spins. We're going to do 3D imaging, okay? Because it's everything in their volume. But for most of fMRI, at least up to now, we want to be able to do 2D imaging, okay? So the question is, how do we do 2D imaging? Okay, and that means we want to excite slice by slice by slice. Okay, so for those of you who've done fMRI, you know that the prescription might be I'm going to do 30 slices, 5 millimeter thick or 4 millimeter thick, the TR repetition time of 2 seconds or something. Okay, so the question is how do we do that and what's going on and what are some of the latest techniques for doing that? Okay, so that's the difference between non-selective excitation, which is this. This is for like 3D imaging. But what we want to do for 2D imaging is we want to just be able to excite the spins in a slice. Okay? And the idea is how do I only get the spins in a certain slice to tip over and leave all the other spins alone? So that's the question. Okay. This is just showing the desired effect. The Z component is here, and the slice thickness is now this. So this is here, we've tipped all those spins, so their longitudinal component goes to 0, and we've excited the slice of this thickness. Right? So what we do is this is where the gradients come in. So the gradients are going to come in. There's really two main things that the gradients do that we'll talk about today. One is creating the slices for us, and the second thing is making the image for us. So incredibly important job for the gradients. When we get to diffusion imaging, we're going to talk about how gradients are going to come back in again. But for today and next lecture, the gradients have a very important job, which is to make the slices for us and also create the images for us. So the thing to remember is that spins precess at their local Larmor frequencies. So the frequency at which they precess is going to be proportional to, is equal to gamma times b, okay, where this is the field. And so typically that B, we have a uniform field, but we also add on this additional field, delta B, which we're going to control. So this is the part now that we control with our gradients. Okay. So just to remind you, that's what the gradients look like. And this is showing you the spins in the presence of a gradient. So this is a gradient here that's going in the x direction. So the field's getting stronger in the x direction and weaker in the minus x direction. Okay. So spins here have some frequency gamma times b naught. If I go out here, these spins are going to precess a little faster. They're going to go at gamma b naught plus some added field. And if I go, over here, these spins are in a weaker field because I've added a negative field, and so they're going to precess slower. So that's the whole idea behind gradients. We make some spins spin faster, and some spins are going to spin slower. Okay? And that's, if you keep that in mind about what gradients do, that's going to take you pretty far in MRI and fMRI. Okay? That's the basic thing that's going on. The gradients are changing the rate at which the spins precess. So here's our next test. Okay? So this is called the Barton pendulum, I think. I only found out about this a few years ago, but it's really cool. So basically, there's 5 balls. So let's call them 1, 2, 3, 4, 5. Okay. So are they all going to swing at the same frequency? They have different lengths of string, right? So they're all going to swing at different frequencies. So they have different resonant frequencies. So in fact, I have a gradient of frequencies. Okay, so these are like spins precessing at different frequencies. Okay, and then I have this guy here, which I'm going to set. It has its own frequency. Okay, so the experiment is this. This is a thought experiment. Let's call this is the RF pulse. So I'm going to set that swinging. Okay, and it's going to swing at some frequency. So what do you think is going to happen to the other balls? Any idea?
They'll align to the RF frequency.
Okay, so will they all start swinging?
I think so.
Okay, so possibly they could all start swinging. Okay. Any other ideas on what might happen? Okay, so let's play the video and find out. So they're just sort of hanging out for now. And then at some point, I think a hand is going to come over here. There we go. There's the hand. And it sets it going. So they're all been strum mode excited. But over time, you notice that there's really only one that's really going back and forth. So basically, it's the one that had the same length as the exciter. Okay. So the same thing goes on in MRI. Is basically if we come in with an RF pulse with a certain frequency, it's primarily going to excite those spins at that frequency, and it's going to leave the rest alone. Okay. But we want to be able to actually excite a slice, not just one line of spins. Okay. So I'm just going to talk you through this, and we're not going to go into the math, but the idea is in fMRI and MRI, we sort of want a slice. We want to be able to select a slice. I want to be able to say I want a slice of 1 millimeter or 2 millimeters or 3 millimeters or 4 millimeters or whatever. Okay. So a lot of the engineering behind MRI is basically how do you get that slice. And so the idea is if I have this gradient field here, so this is the gradient here. So the field's getting stronger here and weaker over here. So this spin here is processing faster, so it's got a higher frequency. This spin here is processing lower, it's got a lower frequency. And then there's some range of frequencies. Okay, and each spin wants its own frequency. Okay, so each spin says, hey, if you give me this frequency, I will tip for you. Okay, so this one wants a slow one, this one wants something fast, this one wants something in the middle. So each one wants its own resonant frequency. So it turns out that I can do that with a very special pulse called a sync pulse. So this pulse, whoops, this pulse has that, still recording? Yeah. This pulse has that property that it has frequencies that are uniform across that thickness. Okay. So that's what. So when people talk about RF pulses, primarily we're using something that looks like what's called a sync pulse. Okay. And so traditionally, for many years, fMRI was done with that. We just excite one slice at a time using these pulses. Okay. Now it turns out that, and this is what it looks like. So we have an RF pulse and we have the gradient pulse played out here. Now, it turns out that over the last 5 years or so, things have completely changed. Okay? And so for all the large studies going on now, it's really switched over to what's called multiband excitation. And the idea here is, if I get even more fancy with my pulse design here, I can actually excite not just one slice, but I can excite slices that are far apart. Okay? So this is a picture from the book. So typically in fMRI, you have what's called either sequential or interleaved acquisitions. Okay? So sequential acquisition might be I excite slice 1, then I go to 2, and then I go to 3. Okay? And I don't skip anything. I just go sequentially. Interleaved might be I go 1, then I skip, and I go 2, and then 3, and I would come back. Let's say there were 20 slices, maybe I come here, and this is 11 and 12. So I sort of skip over slices. Multiband is really different. Multiband means that instead of just here, I just excite one red slice. Okay. Here, I'm exciting 4 slices at a time. Okay. And then I'm going to come along and excite the next set of 4 slices. And then I'm going to come along and excite all the green slices. So all the green slices are excited at the same time. All the blue ones are excited at the same time. And all the red ones are excited at the same time. So why might you want to do this? Like time, right? So in this case, you can go how many times faster? What? 4 times faster, yeah. 4 times faster. Okay, and remarkably, usually when you go faster, you have to give up a lot of what's called SNR. You have to give something up. Remarkably, this has almost no penalty to it. Except you need to buy a coil with many channels to do that. We'll talk about a little why we have to do that later. so you need to, if you don't have a 32 channel coil, you have to pull $100,000 out of your pocket and buy one. Okay, so that's the only downside. And you also need an MRI system that has 32 channels. So if you don't have one of those, you have to pull out another $1 million to get one of those. Okay. All right. Any questions? Okay. So now we're going to sort of talk a little bit about imaging, and once again, only going to give you a brief sort of summary of what it's like, what it is, and just so you have a sense of it. So most of, what we want to do for MRI is we want to look at images. We want to look at images of the brain, but the MRI system actually acquires this data in what's called K-space, also known as Fourier space. Okay, and as you can see from this slide, K-space and image space look really different. Okay, like it'd be really hard for you to sort of think about how to process this probably, okay, unless you have a Fourier transform in your brain. Okay? And most of us don't. So you'd much rather your radiologist look at this image than at the other image. Okay. So we want to just talk a little bit about that so you have a sense of what K-space is. So the idea behind K-space and Fourier transforms is every image that you see can be made up of building blocks that look like this, essentially different striped patterns, where the spacing between the spacing between the slices, the stripes can vary. So here the stripe spacing is getting tighter, and also the angle can vary. So here you're sort of seeing, as we go from here to here, the angle of the stripe is varying. Okay. So what we have here is, in this case, this top row is showing what we're adding to the image. Okay. And then this next row is showing what the image looks like as we add on each component. And so you see we start off with this sort of thing that doesn't look like anything, but by the time we've added all these other 4 components, you're starting to see, well, that might be a head. Okay. If we keep going and adding more components, eventually we're going to get to something that looks very much like an MRI image. Okay. And this bottom here is the K-space. Okay. So I'm going to play this image. Whoops, media not found. Okay. For some reason, this is not going to play. So I'll try to do that next time. Why it's not found. Okay. So let's talk a little bit about K-space, and then we're going to do some exercises. So in K-space, the different parts of K-space represent sort of different edges or different stripes. So along what's called the KX direction, it's the vertical stripes. And then as we move out in the KX direction, those stripes become more narrow. So these are low frequencies, these are high frequencies. Okay. And if we go along what's called the KY direction, we have low frequencies, and then these are high frequencies. Okay. And we can also go off axis, and now we have vertical stripes. And these look like medium frequencies, right? So wherever you are in K-space, if I draw a line to where you are in K-space, you can always figure out what the stripes look like by just sort of drawing the perpendicular lines to that. Okay. And this can be helpful, for example, if you actually, we'll show some examples of artifacts, but occasionally you're going to see an artifact in one of your images, and if you know something about K-space, you might be able to help diagnose what happened. Okay. So let's do a few examples before I give you guys an exercise to work on. So here I've taken a brain image and just done the Fourier transform. So that's the K-space. Now here, what I've done is I've just zeroed out all these parts. Okay. So can you get the lights? Someone turn off the lights? Okay. So if you look at this image, we can really zoom in on this image here. So you notice these edges here, right, have gone sort of blurry, right? Whereas this edge here, these edges here are still fairly sharp. Okay. And so what's happened is we've gotten rid of the information that could represent sort of these vertical stripes, but we've kept the information that could represent sort of horizontal stripes. Okay. Here is an example of some artifacts that you don't see often, but you sometimes see. Whereas you have the brain, you have what's called a corduroy or zebra artifact on it. And so here, you can see there are stripes like this, okay? And if we go here in the, we see there's added energy in K space here. So this corresponds to these added stripes onto the image. In this case, we see stripes going this on the image, and so we see someplace in K space, and if we were to draw an arrow to that, that would give us those stripes. All right. So any questions on that? Okay, great. So here is 4 images on the top and 4 images on the bottom. So I'll do the easy part for you. This one goes with that. Okay. So the rest is there's B, C, and D on the top, and 1, 2, and 3 on the bottom. Okay. And what I'm going to do now is we're going to try using Canvas to do this. So I'm going to open up a survey now. So this is only for completion or not. So don't worry about whether you get it right or not. So I've just published it. Can everyone see Lecture 1, Case Space, Question 1? Okay. So go ahead and you have, I think you have, once you open it, you have 5 minutes to accomplish it. It's not graded, but just, so go ahead and talk with your neighbors, and go ahead and, part of this is also me experimenting with how well Canvas works. So go ahead and enter your answers in, and then we'll discuss what the answers are in about 5 minutes. Okay?
It's just they're doing it. It's not like it's on It won't. They like. Yeah. None of us differ significantly, so they just told us.
Okay, let's finish up in the next minute or so. So if you haven't submitted your answer, please do. It's got 11 answers so far. Okay, this works pretty well. So it looks like we have about 45% accuracy or correct. So we definitely need to talk about this. So there's 3 different K-space images on the top, or images on the top, and 3 different K-space on the bottom. So let's look at sort of the images, and a B, C, or D, which one sort of would you say has the most information in it? D, right? Okay. So which of the K-space below you think has the most information? Right, okay. So even if you knew nothing about K-space, these, you might say that B, D goes with 1. Okay. Now let's look at B. So if we look at B, which are the edges that are preserved? Is it the horizontal edges or the vertical edges? Yeah, so if we zoom in on this, you can sort of see right around the corpus callosum, these edges are fairly well preserved, right? Okay. So if we go to 2 or 3, which of 2 or 3 would be preserving that information? So possibly 3 or 2. It's probably going to be 2, right? Because remember, these things, this has information out here, right? So if I draw a line out to any of those points, it's going to correspond to edges like that. Okay? So B would go with 2. Okay? And then C, if we zoom in on C, you notice here how it's really kept those vertical edges here around the corpus callosum. Okay? And so that corresponds with us, we've kept the information out here, which corresponds to sort of those types of edges. So B goes with 3. All right. So any questions on that? Okay. So, whoops. Keep. Survive. Yeah. Okay. So that's what. So any questions on that before we move on? Okay. Because either one or both of these are going to be on your homeworks. Okay. For multiple choice. So if there's any questions now, ask them. All right. So we don't have time to do these in class, so we're going to assign these for homework. All right. Okay. So what I want to do in the last 15 minutes is give you a sense of how imaging works. So we're going to remind you once again that the gradient fields are there to create different resonance frequencies. Okay, spins process faster where the field is stronger, spins process slower where the field is weaker. And the next concept I want to get to you is what's called a rotating frame of reference. Okay, so we talked about how the spins go 127 million times per second in the 3T scanner. But we don't want to think about the spins going so fast because it's really hard to think about. So we reference everything to the isocenter. So we think about going along with the spin. Okay. So if I'm on like a merry-go-round and I'm looking at someone on the merry-go-round, it looks like they're going around. But if I hop on the merry-go-round, it looks like they're stationary. So imagine if I'm a spin at the center of the magnet, I'm going to assume that I'm going around as fast as that spin. So that spin to me looks like it's just not processing. And all the spins are referenced to that spin. Okay, so that's what we're going to do. So there was also a very famous physicist at UC Berkeley who just died recently who said, there's nothing that nuclear spins will not do for you as long as you treat them as human beings. So it's basically, physicists, MR physicists tend to think about spins and try to think about what they're going to do, like what would the spin do, and so that's what this is referring to. So we're going to do an exercise here. Can you turn on the lights, please? So for this one, I need actually 5 volunteers to come up to the front of the room. Okay, perfectly harmless. So yeah. Okay.
One more.
Okay, so I need you to not trip, make a single file line pointing that way. Okay, great. So these are your 5 spins, okay? So this is really, this is going to sort of give you the basics of how we get the gradients are used to create different spatial patterns in the spins. So we're going to imagine that the Earth's the magnetic field is pointing that way, okay? And spins tend to process clockwise around the field. Okay, so when I say go, I want you to very carefully process. So go. Okay. Great, that's pretty good. Okay, so how was that? Did they do what they needed to do? Okay, and they're in a uniform field, so they actually kept in unison pretty well. Okay, so I'd like you to face towards that wall again. And now imagine you're in a rotating frame of reference. Okay, so when I say go, I want you to process. Okay, so ready, set, go. Okay, stop. So remember, in a rotating frame of reference, you're going. What's your name?
Mariam.
Mariam. You're going. Mariam would be sort of. She's at the center of the magnet. So if we're rotating with her, it appears as she's standing still. Okay. And if we're in a uniform magnetic field, so let's line up again, and we'll say go. 1, 2, 3, go.
Wait, she's rotating?
No,
Or I mean,
she's
we're
not-
rotating, but it looks like she's staying
No.
still.
Everyone's in the same field.
Yeah.
It just happens she's in the center of the magnet. So she won't change at all. What about the rest of you?
I don't know.
Is there a gradient field yet? No. So if you're all feeling the same field, then you're all going to be doing the same thing. So then you won't rotate. Okay. So that'll make things simpler. Okay. So in a rotating frame of reference, it's as if the spins aren't rotating. Okay. So that's the second concept. The third concept is we're going to actually apply gradient now. So we're going to imagine there's a gradient field that's weaker over there and stronger over there, and you have the easiest job because you're at the isocenter. And so the isocenter, when you're doing an fMRI scan, you press the button and it advances to isocenter. It's putting the middle of your object right at the center of the magnet, where there's no added field. Okay, so you have a very easy job because you don't have to do anything.
Yeah.
Okay, you're in a slightly stronger part of the field. Okay, so you're going to process. Every time I say step, I want you to go. Let's see, 90 degrees clockwise. Okay, you're in an even stronger part of the field. So every time I say process, I want you to go 180 degrees clockwise. Okay, and you're in a weaker part, so I want you to go 90 degrees counterclockwise, and you're going to go 180 degrees counterclockwise. Okay, and we're going to sort of we're going to keep track of what the spins are doing up on the board here, so everyone can see it. So right now we have 5 spins. They're all pointing in the same direction, right? So well, we'd say there's really no spatial variation in terms of what the spins are doing. Okay, so now we apply the gradient, and we take our first step. So step. Okay, so I'm going to draw the spins. So let's see. So this spin always stays the same. This one is pointing, let's see, here, right? And then this next spin is here. And this spin is pointing this way. And this spin is pointing this way. Is that right? Okay. So let's say this spacing here between the spins is 1. How long does it take for the spin direction to repeat? How many steps? So this spin is here. So how long before I see another spin that's pointing in that direction? 1, 2, 3, 4 steps. Okay? So here we would say the period is 4. So step. Okay. So this spin is here. This spin is here, 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 here. Okay. So now, how far do I have to move before I see another spin pointing in the same direction as this spin? 2. Right. So now the period is 2. Okay. Step one more time. So now I have this, 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 and this. So what is the period here? 4. It's 4 again. Okay, and step one more time. And so here we're back to no variation. Okay, great, good job, thank you. Okay, so the purpose of this exercise is to show you that if all I do is turn on a gradient, and that's what we're doing all the time in MRI, and I let the spins evolve, I can get different spatial patterns of the spins. And in fact, I can control how quickly the spins, sort of the spatial frequency of those spins happens. Okay. So that's the basic idea behind MRI. This is the basic insight behind MRI that allowed people to make images from the MRI system. So, so this was the in-class exercise we did, and that's just sort of summing up what we did. And so the idea is that I can use the gradients to create spatial patterns and spins that look like that. Okay, so in this case, I've applied gradients both in the x and the y direction. In this example, we only did it in one direction. But sort of if you can sort of extend your imagination, you can sort of think about, if you sort of extend that example, you can sort of think about, oh, I can probably get the spins to be arranged in lots of different directions. All right? And so that's the idea behind the MRI, is we're basically going to make the spins have different patterns. Okay? And each of those patterns sort of is analogous to one of these stripes. Okay? And so, for example, here, I might have a spin, all the spins are aligned. We call this the center of K-space. And then here we have basically variation in the x direction, but no variation in the y. Oh, no variation in the x direction. So any row, the spins are all pointing in the same direction, but along the columns you see a lot of variation. Okay, so it turns out we have this flexibility to just create all these sort of defined patterns of variation. And so what we do in MRI is we go through K-space. So when you're hearing the gradients buzz and you're wondering why it's taking so much time, like why does an MP range take 5 or 6 minutes, it's because we're going through and collecting. And each time we go through, we're arranging the spins in a different pattern, and then we're collecting the data. Okay? So it's almost as if we're taking our object, we're imposing some spin pattern on it. Okay? So we actually impose that pattern of the spins, and then we use the RF coil to listen to what all those spins are doing, and that process is actually equivalent to what's called the Fourier transform. Okay. So every point in time in K-space, we're going bit by bit and filling up, acquiring different points in K-space until we acquire enough of Fourier transform that we can then do an inverse Fourier transform and create our image. So that's the really high-level view of what's going on. And so the idea is that depending on what pattern we have in the object, that summation of spins is going to be different, and it's going to tell us something about the object. For example, if this is my object here, let's say I had this big bar of chocolate, right? And I had this spin pattern. So you sort of see this diagonal spin pattern, okay? And I think of summing up all those spins, you'll see a lot of those spins are going to cancel out. Some are pointing this way, some are pointing that way. So at the end of the day, I don't really have much. Okay, so it's saying that that object doesn't really have a diagonal spatial pattern to it. Whereas if I sort of cut out all these parts of my bar, okay, so now my object is diagonal and my spin pattern is also diagonal. Now when I add up all those components, I get a really big summation, okay? And so that's what the MRI system is doing. It's going through and it's saying, okay, does your object look like this? Okay, if it does, it's going to give you a really big number. And if it goes to another spatial pattern and your object doesn't look like it, it gives you a very small number. We take all those numbers and we put them into MATLAB or some computer software, and that's how we get our image. And that's what the final job of the RF coil is to integrate the signal from all those spins. Okay. And so that's actually how MRI works. We actually go we can move around in K-space. So each of these different patterns is a different part in K-space. And what we do is our basic sequence. So for example, for an MP-RAGE sequence that some of you are familiar with, our basic anatomical sequence, we will use a variation of what's called the spin warp pulse sequence. We're just going to go line by line by line by line through K-space. Okay? And so we're going to acquire one line of K-space, and then another line, and another line, and another line. Whoops. And that's why it takes time. Okay? But in some cases, in fMRI, we don't really want to wait that much time. Okay, we want to be a little more greedy, and so instead of going line by line and waiting, we might want to go faster and maybe what's called like a zigzag pattern and just like zoom through K-space. Okay, and that is actually what the standard sequence is now, is what's called single-shot echoplanar imaging. Okay, where we're just going to excite the magnetization and we're just going to zoom through K-space and collect that data as quickly as possible. Okay. Now there's going to be a trade-off because we only have limited time to collect the data, so we're not going to be able to collect as much data as we would do for an MP-RAGE. So it's going to turn out our image quality, our resolution isn't going to be as good, but we're getting huge temporal gain in temporal resolution, so it's worth it for fMRI. Okay. And finally, to go even faster, we make use of the fact that we have these multiple channel coils. Okay. And so the idea is, because the coils are in different positions on the brain, they each see a different part of the brain. And so we can use that to sort of skip over parts of K-space. Okay? So traditionally, if I wanted to make a nice image like this, I would have to sample K-space with that sort of sampling. If I skipped every other line, so here I'm only acquiring every other line of K-space, I get what's called aliasing. My image folds on itself, and that's not really good. Okay. But if I have multiple channels, I can sort of undo some of that aliasing. And so here, it's showing I can skip every second line, or I can skip, could go 3 times as fast. So here I'm going twice as fast, so skipping every other line. Here I'm skipping 2 out of 3 lines, so I can go 3 times as fast. Here I'm skipping, 3 out of 4 lines, so I can go 4 times as fast. And so it turns out that one of the major things is parallel imaging, which allows us to go faster. Okay, so that's another reason we get these 30-channel head coils. And so some of you, for example, if you're doing an MP-RAGE, there might be an option it's called ARC. So if you see ARC is on, or if the acceleration factor is 2, this is what's going on. We're using the fact that we have these multiple channels to go faster, so we don't have to collect all those lines in K-space. All right? And finally, the thing that's really sort of revolutionized fMRI in the last 5 years is multiband, as we talked about. But think about this. If I excite 3 slices at the same time, my image is going to be 3 slices stacked on top of each other, right? Which is not really what you want to see. Okay? And so, for example, if I do that, if I excite these 3 slices at the same time, this is what my image looks like. It's 3 slices stacked on top of each other. Okay, I can play some tricks and I can move those slices around so they're not totally overlapped on each other, but they're still sort of interfering with each other. What I do next is I use the fact that I have different coils along each slice is seen by different coils, and I can use that to sort of unwrap the slices, and then I can get these very nice looking images here. Okay, so instead of something that's what's called aliased or slice aliased, I end up with taking those slices apart. So this was sort of the technology that was really necessary for multiband in terms of understanding that you could actually do this. And so that's really changed how we do fMRI in the last few years. Okay. So that's all I have for today. So on Wednesday, we'll talk more about relaxation, sort of T1 and T2, and then start our discussion of how fMRI works. And so this is pretty much for the main hardcore physics part of the class. Everything else from here will be more geared towards sort of more focus on fMRI. All right? Okay, so thanks, and see you on Wednesday.